Yeah, so I'm Colin Degraf. I'm a research associate here, and my focus of research is supermassive black holes, looking at how they grow and how they relate with their host galaxies. So today, I'm going to talk about the first supermassive black holes, so the ones that form in the earliest part of the universe that get to be really, really big. So you may be rather familiar with seeing stuff about black holes, including supermassive black holes in the media. This is from several years ago now, from the movie Interstellar, where a significant part of the movie actually relied on looking at a supermassive black hole and getting close to it. A bit more recently, and a bit smaller scale, you may remember seeing in the news about LIGO, using gravitational waves and detected merging black holes. So that's more evidence we have for, yes, black holes really do form and merge and grow. We also have a lot of observational evidence from over the past decade. This is an illustration, but here you have observational evidence of looking at black holes in other galaxies. So, the best evidence we have for supermassive black holes, because before we can really consider how they form and how they grow, we want to make sure we know they really exist, right? So the best evidence we have is in our galaxy. The center of the Milky Way, there's a supermassive black hole, which is called Sagittarius A star. This is looking at the center of our galaxy. This is looking at it using radio waves. And right in the center, right there, that's Sagittarius A star. That's the supermassive black hole at the center of our galaxy. This picture may be a little bit tricky to convince you there's really a black hole there. You see a lot of stuff. It's very bright, but you can't make out exactly what it is. Actually, the best evidence for this black hole is by looking at stars. So this is taking observational data, looking at stars at the center of the galaxy over the course of about, I think this image is over 10 or 15 years. So if you look, all of these are stars, and the ones on the edge of the picture don't seem to really be moving much at all. But the ones in the middle are moving a lot, right? And that's just because there's a lot of gravity there, right? These stars are all orbiting around something. And the closer you get to it, the faster the orbits go. Just like in our solar system. Right? If you get in, as you go closer and closer, and you look at Mercury, it's going around rather quickly, and you compare that to Saturn or Pluto. It's a much longer orbit. So by looking at these stars, we're seeing that same sort of behavior. If we take data like this and look at it another way, here, each of these moving stars is just having a line left behind it, so we can see what path it actually takes. So if you look at all of these, you see we have these nice elliptical orbits. Now, most of them don't have a full ellipse. Most of them just give you a bit of an arc, right, like that, just because it takes so long. This was over the course of 20 years that we see this happen. So obviously getting this to do a full orbit, we would need to wait a very long time. But we're very fortunate there are actually two stars toward the center, which we've observed going in full orbits. So if we take a look at that, this is now just looking at a single image, and here we see these two stars highlighted, and in faint blue there are a lot of other curves. But you just focus on these two ellipses, and there you can see, okay, we know where the stars have traveled, we know how long it took them, and we know what these distances are. So just like looking at the solar system, and you look at the orbits of the planets, we can look at the orbits of these stars and figure out how much mass is it that they're orbiting around. And what we want to do is figure out how much is that. So what we do is we take each one of these stars, start with the ones outside at the very far edge, and see how much mass is that orbiting around. So if you start at the very high radii, so if you start far away from the center, you find out there's a lot of mass inside that. And as you get closer and closer, there's less and less mass, right? Because as you start getting closer, you have fewer stars inside, there's less gas, less dust. So as you keep getting in closer, there's less and less mass. But at some point, that changes. And then all of a sudden, it's just flat. As you get closer and closer, the amount of mass stays constant. And that's because once you're very close, all of the mass is just the black hole at the center. So as you keep getting closer and closer to it, the total mass inside doesn't change. So what we find is that the amount of mass flattens out. What's very impressive is the amount of mass in there is about 4 million times the mass of our sun, or 4 million solar masses. So this is a huge amount of mass, huge amount of matter. And you don't see much there. You don't see stars, you don't see gas. So in fact, this has to be a black hole. And this is what we call a supermassive black hole. It's millions of times more massive than a star. So we find this at the center of our galaxy. We find it at the center of basically all galaxies, in fact. So here you're seeing images of other galaxies, and you see evidence for black holes. So you don't see the black hole itself. A, they're black, and B, it's really far away and there's a lot of stuff in the way. However, you see these jets. And so this is energy caused by matter falling towards the black hole, and then energy is blasted out in a nice directed jet. So here we have evidence that black holes actually exist in other galaxies also. And these are also supermassive black holes. Okay, so I jumped straight into saying, here's the evidence for black holes. We haven't really discussed what they are. What I want to do is talk about the first supermassive black hole. So the first thing we need to understand is, where did they come from? The best way to do that is to look at how stars evolve, what the stellar life cycle is. So you may have come to a talk earlier in the fall where somebody talked about the life and death of stars. And so if you did, that's great. If not, I'll go over really quickly here. So the way stars form is you have a bunch of gas and dust that's able to collapse in. So you have what's called a protostar. Eventually it's able to collapse in, you end up with a star. We have, say, a main sequence star, or a star like our sun. And this can last for a long time, maybe 10 billion years. It all depends on the mass of the star. But the idea is, stars survive because you have a huge amount of pressure, which causes nuclear fusion. And that fusion is going on with hydrogen. So you're smashing hydrogen together to form helium. And that releases lots of energy outwards. So gravity is pulling in, and the explosive force from nuclear fusion is pushing out, and they balance each other. So you have a star of a fixed size. And that's great, except eventually you run out of hydrogen. You can't do that forever. So eventually you run out of hydrogen, and then you can start fusing together higher elements, which can actually push outwards again. So then you can end up with a red giant. The star gets pushed outwards, it's larger in size, and you're burning other elements. Well, this can keep on going, but eventually you're going to run out of elements to fuse together. I'm not going to go into the details of fusion, but basically iron is as high as you can go. So you can't get any higher than that, which means eventually you're going to run out. So gravity is still going to be pulling in, but now there's no more explosion pushing out. So the star collapses. And what happens when it collapses depends on how massive it is. So if you have a reasonable sized star, it'll collapse into a white dwarf. That's a relatively small, relatively dim star. What happens is it collapses in until the force from electrons pushing against each other stops it from collapsing anymore. So you end up with a limited size there. But it's possible to have a star that's big enough so that actually gravity is strong enough to smash together and push past the force of the electrons pushing against each other until you get neutrons pushing against each other. These forces are technically called electron and neutron degeneracy pressures, if you're curious. I want to look it up later. So a neutron star is actually much smaller. Neutron stars, you're talking about things on the order of 20 kilometers across. So it's very, very small, but still as much mass as our sun. But you can take this a step further. What happens if you have even more mass? Then gravity gets even stronger, and it can push past the force of the neutrons pushing against each other. And there's nothing left to stop it after that. Once you get past the neutron degeneracy pressure, it just keeps on collapsing and never stops collapsing. That's how you end up with a black hole. It's just when you have enough matter altogether that just collapses in and never stops collapse. So you end up with something with zero volume. There's never a fixed size where it's going to stabilize. It just goes until you have just a point in space, or what's called a singularity. So basically black holes can be the end stage of stars. Not all stars do. Some you have white dwarfs and you have neutron stars. You have supernova in there as well. But you end up with a black hole. The thing is, this black hole came from a star. So it's on the order of the mass of a star. So it's not quite all we need for supermassive black holes. Just very briefly, you can take a look. Here's a picture of a black hole. This isn't an observational image. This is taking an image, and then this is just using computer simulations to see what would happen if you just put a black hole in our line of sight. So the black hole absorbs all the light, and anything near the black hole gets distorted. So that's what we might expect a black hole to look like. So we just went over, okay, that's what a black hole looks like, that's roughly what a black hole is, and it comes from a star ending its lifetime. But can that really explain supermassive black holes? And that's a harder challenge. So this will give you a sense of just how big these black holes are. So this is when people take observations and try and compare how massive a black hole is with the size of the galaxy that you find it in. And to make this clear, the things at the bottom of this plot are 1 million times more massive than our sun. When you get up here, this is 1 billion times, and these are several billion times more massive than our sun. So these are enormous, okay? So if you just take one of those black holes that forms from a star and try and get to this, you'd need to make it grow to be 1 million or 1 billion times more massive than it started out as. That's a lot of growth it's going to have to undergo. So if that's that growth of 1 million or 1 billion times, maybe even 10 billion times, how feasible might that really be? Well, first thing to do is consider, how do these things grow? So one way would be mergers, right? If you have two black holes that get close enough together, they can merge. You would think that's easy, right? Black holes are very massive, lots of gravity. Shouldn't be too hard if you get black holes close together to merge together. It's actually quite difficult. The problem is black holes will end up orbiting each other. And it's going to take a lot to get them to go from orbiting to spiraling in and finally merging. So actually for many years, people couldn't figure out how that could happen. But then people figured, okay, there are ways to explain that. And if you're curious on that, talk to me afterwards. I can discuss some of that. But we understand pretty well, okay, these things should merge together. And then a couple years ago, we got explicit observational evidence from gravitational waves. So this is showing you all these different mergers of black holes. So each one of these little triplets is a black hole merger. Where, for instance, you have these two black holes that merged together and ended up as that one. On the left, you can see how massive those things were. So these are quite massive black holes to have come from stars. But they're still on the order of a few tens of solar masses. Just a few tens of times more massive than our sun. So that's not really sufficient. You're going to need to, if the growth all came from mergers, you need to have millions of mergers just to form one supermassive black hole. So we don't really expect that that's the only way these things are going to grow. So the other way they grow is what's called accretion. Basically just swallowing stuff, mostly gas. So the idea is black holes are very massive. They have a lot of gravity. So if something gets close enough, it can get pulled in. And that's what this picture is roughly representing. So the idea here is, here you have a black hole at the center. That's that little black sphere. But then you have all this gas around it in a nice disk. And that gas can fall in and reach the black hole, get swallowed by the black hole. And of course, as it goes into the black hole's mass goes up. The more gas it swallows, the more massive this black hole ends up being. So in fact, black holes can grow from being relatively small to being very, very large. Question is, where is that going to happen? Right? So we have already said you can have a massive star that's going to end up as a black hole. But what determines whether a black hole like that grows or just stays at roughly the mass it started out as? Well, mostly it just depends on how much gas is there around it. So if you have a star like our sun, if our sun were turned into a black hole, it won't, it's not big enough. But if it were, if it collapsed and made a black hole, it wouldn't really grow. Right? There's no real gas around us. We don't see gas hitting our solar system. It's not coming in. There's very, very low density, but not very much. So a black hole in our solar neighborhood, in our area, wouldn't really grow. But as you go closer and closer to the center of our galaxy, you start getting more and more gas. So a black hole at the center of a galaxy, that's going to have a lot of gas there. So as long as it's continually fueled, as long as you just keep on putting gas there for it to swallow, it can keep on growing. So it's really just the center of galaxies that these things are going to grow like that, which is why we typically would expect one supermassive black hole per galaxy. You have one at the center. Other black holes can be there, and if those black holes get in toward the center of the galaxy, the black holes will merge together. You're still left with one. Now, when galaxies merge, you can end up with two supermassive black holes. But eventually those two supermassive black holes will get close to each other. They will merge. So typically speaking, we find a supermassive black hole per galaxy. So we've figured out, okay, we know they can grow. If they're found towards the center of a galaxy, you can have a lot of gas that they can swallow. The question is, can they grow enough? So this is an important observation that was made in 2011. So this is the spectrum of a supermassive black hole. We're not going to discuss how you measure the spectrum, how you determine it's a black hole. There's a lot of interesting stuff in there, but we don't have time for that. So for the moment, just take my word for it. This is the spectrum of a black hole. What's really important about this one is it's really far away. So if you're familiar with redshift, it's at redshift 7. That means it's so far away that what we see of it is when the universe was only about 750 million years old. Okay, that sounds like it might be a large number, but since the universe is almost 14 billion years old, that means we're seeing this supermassive black hole when the universe was very, very young. What's more, this black hole is about 2 billion times the mass of our sun. So that's telling us somehow this black hole needed to form when the universe was very young and then grow to be really, really big. So the question is, how do you do that? How can you have something form and then grow to be that big when the universe is still that young? Well, to consider that for a minute, let's try and figure out, is there an upper limit on how fast a black hole can grow? So obviously a black hole with no gas around it will not grow at all. There's no real lower limit. But is there a maximum rate that these things can grow at? And to take a very simple picture, just imagine a black hole, that's that little black thing in the middle, in a whole bunch of gas, which is all that yellow. Well, there's gravity pulling the gas in towards the black hole. So it's going to fall inwards. But as that gas falls onto the black hole, it emits radiation. And that radiation goes out and pushes on the gas trying to fall in. And so what happens is you have gravity pulling in, but you also have radiation pushing out. The question is, which one's stronger? Well, the more gas falls in, the faster it falls in, the harder the radiation pushes out. So that tells us at some point there's an upper limit on the rate at which the gas can come in, at which point the force pushing out actually equals the force of gravity. So if you just set those two things equal to each other, that gives you an upper limit on how fast gas can fall in. And that's called the Eddington rate, because Arthur Eddington is the one who figured that out. He calculated this. So if you plug in the numbers to the equations you get from doing that, you find that it could double in mass about every 35 million years. Okay, so every 35 million years, that's a long time. But to double in mass, that means if something is already a billion solar masses, it could double in just 35 million years. The problem is, if it's only one solar mass, it might take 35 million years to get to 2. Right? But this tells us, okay, we have an upper limit. This is approximately, we can say, let's assume this is the fastest a black hole can grow. Well, does that work? Well, we can do a very simple calculation. So these are two different black holes that have been observed in the very early universe. So when the universe was about 690 million and about 750 million years old. And we know their masses, so that's what tells us how high they are on this chart. So then we can say, okay, well, let's take that and assume that it grew at the fastest possible rate. What does that tell us about its history? And we just put it in. Because you can calculate this Eddington rate, which tells you exactly how fast it had to grow. And so it tells you it must have had that history if it was growing at this maximum rate. If you assume that it was growing at 75% of that rate instead, then it would have looked like this. So it's growing at 75% instead of 100%, then it had to be a little bit more massive at any given time to get there. Here's the problem. This is how old the universe is. So that tells us for this to get there, when it formed, it needs to lie somewhere on that line. That's if it's growing at that maximum rate. So what we're basically saying is these black holes had to form somewhere in that region. And if we look on this chart, that's on the order of 1,000 or 10,000 or even 100,000 solar masses when it first formed. So that's a bit tricky. So what we want to do is say, okay, we already discussed how black holes formed in the recent universe. They come from stars, but those are going to be on the order of 10 solar masses, not 1,000 or 100,000. So what we want to do is consider what's different about the early universe and how can they form. How would they form then instead of what happens now? And the short answer is we don't know, but we have some ideas. So I have three main ideas. One of them is that these black holes come from the first generation of stars. Well, those first stars were bigger than the ones we find now, because when those stars formed, they were able to collapse from a large cloud of gas that doesn't break apart. It just ends up one big star. So it might be hundreds of solar masses. So that's one way they might have formed. Still only hundreds of solar masses, so that's a little bit tricky. Another way is you have a dense nuclear star cluster. So that's saying a cluster of stars at the center of a galaxy. You have lots of these stars, and those stars can interact with each other. And they can start colliding with each other. And they get bigger and bigger until you end up with a supermassive star that can then collapse to a black hole. That might be 1,000 solar masses. So that's an improvement. It's getting to be more massive. Then there's the third case, a direct collapse. So in this case, we're just saying, just take a really big cloud of gas. And if that cloud of gas can collapse just straight into a black hole, and don't break apart, don't form a star, just collapse all the way to a black hole, then that can actually be on the order of 100,000 solar masses. So that might be able to explain it. So basically we've got these three cases, right? First generation of stars could turn into it, but those would be hundreds of solar masses. Might be relatively common, but hard to then grow so much. Case two is nuclear star clusters, 1,000 solar masses, which is an improvement. And then you have direct collapse, which can give you 100,000 solar masses. The problem is the conditions for this are very rare. So we have these three different possible ways of forming. This one, very low mass, which means it's hard to grow to be so big, but relatively common. Out to this one, which is a very high mass, but also very rare and hard to find. So we have this range of possible formation mechanisms, which is both good and bad. Right? The problem is we still don't know which one of these is the right answer. Right? I can't tell you, I'm not hiding it from you. People are still trying to figure it out. This is one of the things I'm trying to figure out. Right? So any of these three are believed that they might explain it, but we haven't figured out for sure which one it might be. Okay, so I just said there are three different ways we might be able to form a black hole in this area. Some of them are a little bit lower than that, but okay. At the very least, a direct collapse black hole we do expect to be about this mass. So it could form up here, that's fine. But there's another question here, right? And that's, well, what about all this? To get to be that massive, you need to start out here. Direct collapse can do that. Nuclear star cluster could probably do it. Population 3 star would be a little bit tricky. But it is quite possible. But once you get here, you then need to grow all the way to there. You need to grow to be 10,000 times bigger, at least. Right? And that's just going to take you up to about here. So we're talking about a huge amount of growth. And I said this is the maximum rate it can grow at. But that's if you have lots of gas there. You still need to have that gas. Well, it turns out that might be possible to do as well. So here's an example of how you might be able to do that. So here's a galaxy, and here are three different streams of gas that are just constantly flowing onto that galaxy. So this is an illustration based on simulation work, which finds we do expect you should have gas flowing onto a galaxy. And for somewhat complicated reasons, you expect it to typically come in three different streams. So you can have this gas coming, reaching the galaxy. But the black hole's at the center of the galaxy. This gas is coming from outside the galaxy. What happens as you approach it? Well, this. Right? So this is an illustration, but this is an illustration of a capsule re-entering Earth's atmosphere from outer space. Right? And you have all this bright red, and you see this sort of red. That red is from the atmosphere, the air, which is heated up. What's happened is, as the front of this is hitting the atmosphere, you're pushing the gas together, and as the gas hits more gas, it actually gets hotter. So this can be what's called shock heating. So you're basically pushing gas against other gas, and it heats up. And when it heats up, it's going to stop falling onto the galaxy. So we find that with galaxy simulation. So this is a little bit of an odd picture, but basically this is a galaxy in the center, and then all the rest is gas, and the color is telling you the temperature. And so what you have is, you have out here, you have cold gas, and in near the galaxy, you have hot gas. So whenever this gas is coming and getting close to the galaxy, it's going to start approaching, it's going to hit that hot gas in the center, or not at the center, but as you start getting close to the center, and it's going to heat up. And what that ends up doing is you get a shock right here, and another one over here, and that gas slows down a lot. It essentially stops coming in and falling onto the galaxy. So you have lots of gas flowing in, but it only comes to about here, and then it stops going. So if that's happening, then the gas at the center of the galaxy that the black hole can swallow is going to run out. The black hole is going to swallow a lot of it. It's going to emit radiation, and some gas will form stars, but eventually you're going to run out of that gas. The black hole can't keep on growing. So the only way you can manage this is you're able to provide more gas somehow. And the answer is actually also on this same figure, and just right over here. So yeah, we have this very cold gas coming, and it hits this shock. But you also have some cold gas that's actually able to come all the way in. So what happens is, if you have basically a stream of gas that is really dense and really cold, it's able to penetrate, go through that shock, and keep on going all the way in towards the center of the galaxy. And if you manage to do that, then you're able to actually form, you're able to fuel that black hole. The question is, how often would that actually happen? That's really hard to figure out, because it depends on lots of conditions. One of the best ways to determine that is just use a simulation. So you do a really, really big simulation that has millions of galaxies. And you want to see, do any of those satisfy these kinds of conditions? So that's been done. And here's an example. So this figure shows going from the early universe going towards the more recent universe, just the mass of several different black holes. And in this simulation, you find there are black holes that start out relatively low mass, but then they grow very efficiently for a very long time, and end up actually reaching 1 billion solar masses. So what we'd like to do is look and see, well, how did that happen? We take a look. We're just going to focus on this one black hole. And in the very early universe, when the mass is still relatively low, this is what the temperature of the gas around it looks like. So you can see, it's not too hot yet. Red is hot gas, so it hasn't really started getting too hot. But it is starting to warm up in this area around the center. And as more time passes, you get to be more massive. Once the black hole is about 100 million times the mass of our sun, this is what the gas looks like. So you do have some hot gas in the center. You can see that orange color. But you also still have some gas coming in from these streams that's able to keep getting in. And eventually, you start getting very hot gas in this red, but you can still see that some of this gas can come in to get very close to the center. And so that's able to keep on fueling this black hole. And as long as it's able to keep fueling it, it's going to keep growing, and eventually it'll reach about 1 billion solar masses. And then after that, then you have this gas, this hot gas keeps on expanding out. Eventually it stops the gas from coming in. So now you no longer have any gas coming in from the outside. And that's why this is flat. That flat is saying black holes basically stopped growing. The gas around is too hot. The inflowing cold gas is not cold enough to actually penetrate anymore. And that gets even more extreme at the end. So within this simulation, we actually looked at several cases. So each row here is a different black hole. And you can see it's the same kind of behavior in each one. You will have this cold gas coming in, very nicely seen right here, that can penetrate that hot gas, get all the way in and fuel the black hole, which lets the black hole keep on growing and growing. Now, just to be clear, here are 3 black holes that got to be big enough to be 1 billion solar masses in the very early universe, like we've observed. There were millions of black holes in the simulation, which did not get to be big enough. So I'm just picking and choosing the ones that are in the right conditions for you to see this. But it shows us that this does seem to be quite possible. So you actually can have a very long-term growth at that maximum possible rate, that Eddington rate, which would let you get to be that massive in the very early universe. That's not the only explanation, right? There are some other proposed things that can help. So I said the Eddington rate was the maximum rate it could be, but that was making several assumptions, right? That was saying, well, what if the gravity pulling in balances the radiation pushing out? Well, for one thing, what if the black hole is moving? Then it doesn't need to have gas fall in on it. It can move into the gas. So if you have a black hole that's just moving around following this black line, it can actually accrete even faster. And it'll grow even quicker. Another thing is just going back to the picture we looked at before, which is the black hole's in the center and you have this disk of gas. Well, I said that the Eddington rate is when the radiation out stops the gravitational pull coming in. But in this case, all the radiation, or most of the radiation, is going this way, but most of the gas is over here. So you can actually grow even faster if you have the radiation push that way and pull in gas this way. So you're actually able to grow faster than that Eddington rate. It can be challenging, requires certain conditions, but it is possible. So that's a way that we can actually grow even more efficiently and get us to those very high masses very early. So basically, the challenge with supermassive black holes in the early universe is they're really big and they have to get there somehow. And we're still working on this. There are lots of unanswered questions. Lots of people are still studying this. But the best we can say at the moment is you need to start out by forming a very large initial black hole, bigger than the ones we would find now from just stars collapsing at the end of their life. So you start out with a pretty big black hole, and then it needs to grow really rapidly for hundreds of millions of years. But that in the end can get it to be one of these really supermassive black holes.